Okay, in this question we've got two objects each holding a charge. One of the charges is given. On the larger object it has a charge of 16 microcoulombs, and the goal originally was to find the charge of the smaller one, the 0.05 kilogram sphere, if it's 10 centimeters away from the larger one. And the information they give you is as follows. When this smaller one is released, it accelerates away, so it's being repelled from the larger sphere at a rate of 1,150 meters per second squared. Now right away, if it's repelled, we know that the sign of this charge must be the same as the sign of this charge, because like charges repel. So if this thing has a positive charge of 16 microcoulombs, Q will also have to be a positive charge as it accelerates away to the right. And we saw that in part A. Now, as with any question involving forces, it's basic dynamics. And the first step with dynamics is to construct free body diagrams. Now, I've got two spheres here. The one that's accelerating, the smaller one, labeled in red here, is the one we're going to focus on. But let's start by labeling the forces acting on each sphere and discuss. Okay, we're talking about electrostatic repulsion, so I've labeled each force with an Fe, the E standing for electrostatic. So I've got a force acting on my little red mass of Fe1, pushing it to the right, and that's the repulsive force due to the 16 microcoulomb charge on the left. And there's a force labeled F electrostatic 2, or Fe2, pulling the 16 microcoulomb mass to the left. Now these forces, according to Newton's third law, are equal and opposite. Now because this mass on the right is much smaller, it will be more affected by the force because it has less inertia. So for this situation, we can imagine that this one on the right is much, much larger and is going to remain basically stationary throughout this process. It's not critical that we imagine that, but it's easier for the concepts if we do. So initially we're 10 centimeters apart, and the only force that we're worried about acting on this charge is Fe1, so the force of repulsion between these two. And since that's the only force we worry about, that is my net force. So I can write my equation of motion as follows. So we see our equation. F net is, as usual, the sum of the forces that are parallel to the motion. And in the case of the object on the right, there is only one force acting on it that we're worried about. So my net force, or my unbalanced force, is provided by Fe1. There's no other forces, so that's it. Now we can go ahead and substitute in for F net. Newton's second law says that F net is always ma. And Fe is governed by Coulombs law. So let's write those equations in now. So this represents our equation of motion. F net is ma, mass times acceleration, and our electrostatic force is governed by Coulombs law for point charges. Point charges in physics are spherical balls of charge, and it's governed by K, Q1, Q2 over R squared. So that's our equation of motion, our general equation that represents this particular situation. Now I can take it one step further and solve for A, and then we can analyze the question. So we can see that the equation actually tells us quite a bit. Our acceleration is directly related to the size of the two charges, which makes sense. If these two charges got bigger, in other words, there was more charge stacked onto the outer surfaces of these two spheres, they would repel each other with greater vigor, and it would fly off at a higher acceleration. So acceleration is directly related to Q1 and Q2, meaning if I double the charge of Q2, I would double the acceleration. And if you're savvy with the equations, you can see that because the Q1 is on top, as is the acceleration, and they're on opposite sides of the equation. Now mass and radius are on the bottom of the equation. So we say that those are inversely related to my acceleration. If the mass of this little red sphere suddenly increases, it's going to have way more inertia, and it's not going to accelerate as rapidly. That's Newton's second law. So again, that makes sense. The distance, however, is the one factor we haven't really talked about. And as this object gets further and further away from the 16 microcoulomb sphere, the force gets weaker. Remember, force is KQQ over R squared, so it gets weaker by the square of the distance. In other words, if I double the distance, my force is diminished by 2 squared. My force is quartered. If I triple the distance, 3 squared is 9, my force is 1/9 what it was originally. So my acceleration is also diminishing with R squared. So it's still accelerating, you have to remember that, but the acceleration is smaller and smaller and smaller as I get further and further away. It's going to continue to speed up. That's what the acceleration means in this case. It's in the same direction as the motion, but it'll speed up to a lesser extent as it gets further and further away from that large sphere. So it's going to continue to have a positive acceleration to the right in this case, but the acceleration is going to be decreasing as you move away. Your velocity is always going to be increasing, however. It gets complicated. What would the graph look like if I made a graph of acceleration versus r? So we see that since acceleration is proportional to 1 over r squared, I'll get this inverse relationship on my graph. As r gets bigger and bigger and bigger, the acceleration continues to get smaller and smaller and smaller, always positive.